Okay, so you know, the way I like to run my review sessions is mostly just practice some problems. You guys already have a lot of problems to be looking at. I'm sure you are. The main things you should be looking at are, of course, the group works, the practice quizzes, the review packet that has some questions at the end of it, as well as the sample test, which is actually a test that I've given in this class before, kind of at this point in the semester. So it lines up pretty well. I think the problems are well aligned to chapters 2, 3, 4, and 5. So that's all good stuff. And then I'm going to give you some more problems today. So we're going to actually solve different problems. The whole purpose of this really is, that makes this different from just studying on your own, is we're going to be solving them in real time, which is good because you're going to have to do that on Monday as well. So practicing kind of thinking on your feet, so to speak, is part of what you get out of this. And then, of course, you can always go home and practice these again later on your own time if you need to go back and review some stuff. Remember that this is going to be a no calculator test, so we're just going over the basics. So I don't want to see 25 people walking in with their calculators ready to go on Monday and then like, sorry guys, don't get to use those. No calculators, which means obviously I'm going to make the numbers reasonable, but a few people have been asking me about that. I mean, if I gave you a number like 1 million and asked you to divide it by 7, I would expect you to be able to do that and come up with a remainder between 0 and 6 relatively easily. 1 million might be a little bigger than I need to make it, but I'm going to try and make problems that you can't just by inspection see the answer to. So if I make my numbers too small, well then it defeats the purpose of having you use what you've learned in the class to solve the problems. So the numbers will be big enough that you're going to have to think a little bit about what's going on. And then also don't forget to be learning those theorems. There are, theorems slash propositions, I guess you could call them. They are listed in the review packet. I actually have not listed them out ever in class here, but they're in the review packet. So be sure to do that. You don't have to learn them all. You have some choices. And you guys are math people, so I figure there's 5 of them, and I'm going to ask 2 out of 4 on the test, so you can do a little calculation how many of them you really need to learn. You should learn enough. Don't gamble on this, okay? Study enough theorems that no matter what I put there, you can make sure you're going to get it right. And we're going to start like 5 minutes early on Monday. I'll get everybody started, and you guys should really just knock those out first. That's really some free points. About a quarter of the exam is going to just be doing that. So I'm expecting everybody to get really close to perfect on that. I will also grade those proofs, though, a little bit more strictly than everything else where you're doing it right on your feet, because you've had time to really understand and learn the proofs carefully. So please do that. And I would suggest you just do the burst and kind of do it in 10 minutes if you can, 10 to 15 minutes, be done with that, and then you can go on to everything else. As far as the rest of the test goes, you should expect a mix between computational problems where I'm asking you to just solve something like I don't know, Fermat's little theorem application or something like that. And then also a mix of sort of theoretical problems. So something like the one that I put on the board over here would be kind of a small theoretical problem. The problems that are theoretical will be short enough and small enough that I would expect somebody could work them out even if they didn't actually study them. So obviously the proofs that you're learning that are from the review packet, those are pretty long proofs. That's why I'm telling you in advance that you need to know them. The other results that I ask, so I could ask you to prove something like this because the proof is fairly short, right, and just uses the elementary material and doesn't take that much space. So you shouldn't be expecting, other proofs that are also, like a whole page in length. Sometimes I will space out the questions on my own paper. So if I give you like an inch of space to solve a problem, probably means that's all you need. It's going to be something pretty quick. And the point values on the problems are aligned with how much time is involved in solving them. So a problem that is worth a lot of points doesn't necessarily mean it's a hard problem, but it means it's a problem that takes more time to solve because there's maybe a lot of steps involved. A problem that's not worth very many points might actually be a fairly hard problem, could be, But once you know what you're doing, it's very short to write it out. So it's based more on the length of solution than the difficulty of the topic. Okay, I'm going through this because some of you have not had me before, to make sure you understand what my mindset is when I'm writing these questions. So, okay, so are there any questions about that, the format, or anything like that? Yeah, Lisa?
From this session, besides uploading the video, will you also upload the sheet of the problems?
I probably will not have time to write up solutions to these problems. I would love it if anybody here is kind of good at note-taking, to take notes, I could post them. You're nodding? Okay, well, yeah, there you go. So I got somebody, I might, if you don't mind, borrow them, and then I can just scan them in and put them up. Does that sound good? Normally I would do it, but I don't think I can get it done in a short amount of time. I haven't taught this class. The last time I taught this class was like 6 years ago. I was barely, I was like brand new practically, so I wasn't all organized about my stuff the way I am with some of my other classes that I teach more regularly. So just don't have it all together yet. Okay, so any other questions before we dive in? So the plan for the rest of the evening is just practice some problems. They're going to kind of jump around a little bit, and just to give you a feeling for what kinds of questions I'm going to ask, okay? Just because you understood every solution to every problem I present doesn't mean you can just stop studying and you're ready for the test. But on the other hand, if you find some of these problems challenging, it's a good guidance for you as to what you need to focus on in the next 36 hours or so, or 48 hours or whatever it is. So this is a nice problem. I've actually kind of alluded to this one before, so I would like to prove it so I can feel really good about the fact that we went over it. So if you have a common multiple of A and B, then of course the least common multiple by definition would be less than or equal to any other common multiple. But this is actually a stronger problem, which is saying prove that it actually divides this other common multiple. Okay, so obviously M is going to be at least as big as the least common multiple of A and B. Okay, so this is a kind of an application that we can start off with. So does anybody, while I was running up and down the elevators, did anybody come up with any suggestion on how we could maybe approach something like that? We have an idea. Yeah, Lisa?
Since M is a common multiple of A and B, then M equals AK and M equals BL for something else.
Okay, so we may as well write down what we know, okay? Which, by the way, is a good piece of advice also for my test because I give partial credit. So if you write down things that are relevant and true and important for the solution, you'll get points for those even if you don't put the pieces together properly. It has to be relevant, though. Make sure you're not just writing down something that's true about, calculus. Yeah, that's great. They know all that stuff about calculus. It's not gonna get you very far. Okay, so let's write that down. So we know that M, which is a common multiple of A and B, would be like A times K, and M would also be B times L for some integers K and L. Okay, so we certainly know that. Okay. Any other thoughts? So here's a little tip. Okay, first of all, I'm going to make a notation for the LCM. So let's let I don't know what to call it now. Let's let C be equal to the LCM of A and B. Okay. Yeah, please.
Right now, I was just trying to think, if we did want the least common multiple based on the GCD, we could set one of the formula to give them common multiple.
Oh, yeah. Does anybody know that formula? Because it's worth mentioning. So that there is a relationship between the LCM and the GCD. Yeah, if you multiply these two things together, you end up getting A times B. Right? Everybody knows that. That should be from your notes. Right? So we could turn this problem around into a problem about the greatest common divisor by using this equation to kind of bring that into play. We could do that. I'm glad you mentioned it because that's an important fact to know. here's another tip. If you want to show that one number divides another number, a good way to do that is to actually divide the one number by the other number and try to prove that the remainder is 0, right? So that would be, I think, a good approach to this problem right here. So, and by the way, what is that process by which we take one number divided by another number and get a quotient and a remainder? Good, the division algorithm. Very good. So by the division algorithm, let's see. What we can do is we can write, the division algorithm allows me to write m as some multiple of c. So this would be, let's say, q times c plus r for some integers q and r with, what's the condition that we need to state here? Right, 0 less than or equal to r less than whatever we divided by, which was c, right? Okay, so we would get something like that. Agreed? Okay, so we have that. Now r, notice what r is. So r is equal to m minus qc. So if we think about that, m is a multiple of a, and c is a multiple of a, right? C is a common multiple. It's actually the least common multiple of a and b. So actually, m is a multiple of a, and c is a multiple of a. So therefore, r is a multiple of a, right? So since m and c are multiples of a, r is a multiple of a. So I could actually just write it this way. R is a multiple of a. Also, see, let me just back up for a second. So C is the least common multiple of A and B. It's the smallest thing that's a common multiple of A and B. What am I trying to prove right now, by the way? At this point, I just want to motivate this instead of just telling you stuff. Let me just motivate. So I did this division algorithm in the hopes of showing what? R is 0. If I can show that r is equal to 0, then I will know that c divides m, which is what I'm trying to prove. Right? So I would like to show that r is 0. So here's the thing. We know that r is less than c, and c was already the smallest common multiple, the least common multiple of a and b. So if I could show that r is also a common multiple of a and b, that would be sort of a contradiction. I mean, c was supposed to be the smallest common multiple of a and b, and now you've got this other number r, which is smaller than it, that's also a multiple of a and b. And the only way that that would be true would be then if r is 0. Okay, so also m and c, everybody agree they are also multiples of b? So r is a multiple of b as well. Okay, r is a multiple of b. So r is a common multiple. R is a common multiple of a and b. By the way, guys, we have some more pizza. Don't help yourself. You guys on the video, you're missing out. They did this to me. You know, we were hiring new people in the department like a year or so ago, and we were doing the phone interviews like in the middle of December. I went home for Christmas and everything. The rest of the hiring committee was sitting in the room, and we were doing Skype and everything, and talking to the candidates, and they were all sitting there eating all this food. I'm sitting over in Nebraska starving to death. So today it's my turn to tease people about it. Okay, so R is a common multiple of A and B, but by definition, C is the least common multiple of A and B, and R is smaller than that. So the only way we escape from a contradiction is if R is equal to 0. Okay? So R is equal to 0. That's because the least common multiple has to be a positive number. So, this is an acceptable conclusion. If R was any other number, like 1 or 2 or 3 or 4, we would have a smaller common multiple of A and B. But 0 doesn't count, is what I'm trying to say. 0 doesn't count as being a smaller common multiple of A and B. Okay, so a problem like this, I might give you a hint and say use the division algorithm. But anytime you have like one number and you're trying to prove it divides another number, a reasonable approach would be to take the one and divide it by the other and see if you get a remainder of 0. Okay? You could also think about doing things in terms of mod. I mean, you're really trying to prove that M is congruent to 0 mod C, right? That's just a rephrasing of the thing that you're trying to prove. But sometimes looking at things in modular arithmetic world is more natural for you. Divisibility is sometimes a little bit slippery. Okay, so far so good. Let's take another problem. I'm going to write it right below the first one because it's related to the first one. So here's number 2. This is along the same lines. Here it is. If C is a common divisor of A and B, so if C is a common divisor of A and B, then C divides the GCD of A and B. Okay, so this one involves the GCD. It's sort of like turning problem number 1 around. Okay? Not only are these proofs kind of important to be able to do because they're fairly elementary and using the basic concepts, it's also important to kind of have the big picture of what we're saying here. What we're saying is that we have 2 numbers A and B. We can go up to their LCM, which is the smallest common multiple of the 2. And what problem number 1 says is that any other common multiple would be above it, right? It would be actually divide into it. So this one is a divisor of all other common multiples. But then we can also go the other way. I think this picture is actually kind of helpful in terms of understanding the concept. We can also take the greatest common divisor. We can shrink down to the biggest thing that they have in common. And then what this problem is saying is that any other divisor of both A and B divides into the GCD of A and B. So it's kind of a picture to show the relationships. Okay, yeah, Brandon?
Isn't that true by definition, though, of the GCD?
The definition of the greatest common divisor of 2 numbers is it is a common divisor of those 2 numbers such that any other common divisor is less than or equal to it. So there's no divisibility in it. If you go back to the actually that's the definitions. Okay, so not only are you going to have pretty much 25 or so easy points learning the theorems and the proofs. Also, I may ask you for some definitions. I consider those to be kind of giveaways as well. So those are supposed to be the easy things. So you should know those kinds of definitions. What's the definition of the GCD of 2 numbers? Exactly. So the definition is that in order for something to be the greatest common divisor of A and B, it has to be a common divisor, and any other divisor has to be smaller than or equal to it. We could write that all out, but it's in your notes. Right? So let's definitely go back and make sure you know that. Okay, so let's try and do this problem. Anybody have a suggestion as to how we might want to start this? This one's actually easier than problem 1. Derek, go ahead.
So you would just say that A equals CK and B equals CM for some K and M and Z.
B equals CM. So for some K and M and Z, and by the way, I really like how you emphasized, okay, the quantification is important. I probably won't, on a test I'm a little more gentle than I am on grading homework. But not putting quantifiers on things and just having variables show up out of the blue is not good form for proof writing, so you do need to explain it. Obviously, the letters that are already in the problem don't need an explanation and don't need to be quantified, but as you bring new variables and introduce them into your solutions, they should always be quantified as whether it's for some or for all, and so on. Okay, so this would be great. Okay, so A is a multiple of, so C divides A and C divides B. That's basically what we have there. Okay. Let me give a name to the GCD, just so, again, we don't have to work too hard. So I'm going to let D be equal to the GCD of A and B. Can I erase this picture in the middle? It's a good one to... Of course I can, because let's go back to the video. Okay, so there you go. So D is the greatest common divisor of A and B. Okay, so what else could we say? Very good. Can you say that a little louder, because that's the key point?
You write D as a linear combination of it.
Exactly. So the GCD of A and B, one of the first things that should always come into mind is that it's expressible. This is one of the theorems that you're learning, right? So it should be on the forefront of your mind. I think it's theorem 2.3 says that the GCD of two numbers is expressible as a integer linear combination of them. I'll write it as AX plus BY, and again, I have to quantify that for some X and Y and Z. Okay? So we have all that, and we're trying to show that D is a multiple of C. That's the one?
Just plug in CK and CR.
Exactly, just plug in for A and B here, right? So A becomes CK, and B becomes CM, right? And then you just have C times KX plus MY. And then that implies that C divides D. You guys can use some symbolic notation as much as you want on a test. I want you to be able to go quickly. You don't have to write out anything too, especially on everything that's not the proofs that you're learning. Just the new problems, things like this, you can go very quickly through them. I don't need you to say things on the homework. I really appreciate it when people stop and say things right here like kx plus my is an integer. Because technically, to say that C divides D at this moment, I would need to say that. But I view that as being basically clear because K, M, X, and Y are all integers, so therefore this whole thing is an integer. You don't need to say that on the test, okay? It's going to take too much time. Okay, so that's it. Not too bad. Not too bad. I think that's a pretty reasonable little problem. Okay, are we okay on that? Okay, maybe we should do something maybe a little bit more computational. So I'm going to show you a mixture of things, right? So these are a couple of little proofs. Let's do something a little more computational. The computations, of course, we have, Diophantine equations, linear congruences, we have the Chinese remainder theorem, the Fermat's little theorem, Wilson's theorem, some of these more recent things that are kind of computational. So let's see if we can, I'm on number 3, I believe. Let's see if we can work out an example of this. So let's find the 3 smallest positive solutions to 140 times x is congruent to 133 modulo 301. That might be so this is kind of the size of numbers that I kind of want to use because it's big enough that you're not just going to like plug in something and it works right away. There's too many things, you've got 301 possibilities. It's a little too many to do. I will be writing the test with the mindset that you're going to solve it, using the sophistication of the course. So if you want to spend, 75 minutes plugging in 301 guesses for x to get the answer, you might get it, but the rest of the test is not going to happen, right, if you spend too much time on it. So you need to do this in a more sophisticated way. Okay, so what would be the first thing you'd want to do with this? Say it one more time, I'm sorry.
Find the GCD between 140 and 301.
Oh, okay, good. The 140 and the 301, this is very important because remember guys, this is one of these congruences of the form AX congruent to B mod N. If the GCD of A and N doesn't divide B, then we're done, and there's no solution at all. Remember that? So that would be a good first step, is to figure out what is the GCD between A and N. So this is, so for the solution, we need the GCD of 140 with 301. And okay, and so how do we then go about doing that? We do the Euclidean algorithm. So I'm going to do this. This is probably the only time today I'm going to do this. Just do it one time to practice it. We just put the bigger number on the left usually. That's the way I like to do it anyway, 301. How many times does that go into 140? 2 times with 140 with what remainder? 21, okay. So we have that. Then we take the 140 and we want to multiply it by 21. So how many times does 21 go into 140? 6 times, right? The way I look at it, you know, it's about 20, right? It's about 20, so it should go in about 7 times, but it doesn't quite go 7 times because this is 21, so it must go 6 times. If you put 6 in there, you get 126, so there's a remainder of 14 at the end of that. Now we move the 21 over here. We divide it into 14, and we get what quotient and what remainder?
7.
What quotient? 1 times 14 plus 7. Very good. Okay, and then the next step is going to be 14 equals 7, sorry, 2 times 7 plus 0, right? So the GCD, as you remember, is the last non-zero remainder. So it's 7. So the very first thing I would want to do at this point is see if 7 goes into 133. Because if it doesn't, we should just stop right now. Okay, so 133 into 7, does it work? 19 times, right? Okay, so 7 does divide 133. Check. Make sure you're writing these numbers in the correct order, by the way, all the time. The smaller number on the left, the bigger number on the right. Okay, so we know that there are solutions to this linear congruence. What can you tell me, what else does the theorem that pertains to linear congruences tell us about the solutions? Kevin?
There's 7 solutions. 7 incongruent solutions.
Modulo 301, exactly. Okay, so we could just continue to work with the congruence this way, but in other words, stick with it in the world of mod 301. But what else could we do that makes this, that I personally think makes it a lot cleaner? Exactly. You now know that there's a factor of 7 in everything that you see, so just take it out. Take the 7 all the way out of it. So divide by 7. You can always do this, right? This is not something you have to worry about, ooh, can I do it or can't I do it? You can always do it, right? This is a good thing. So if I divide by 7, I get 20 times x, congruent to 19, modulo, let's see, how many times does 7 go into 43 times into 301? Okay. So here's our new problem. It's a little bit smaller, but I think it's probably still a little tricky to just eyeball the answer. So we're going to have to work a little bit more. Okay, so with this new problem, well, what is the GCD now between the, what is the new GCD between the coefficient and the mod? 1. It'll always be 1 because you're dividing out by this common multiple, I'm sorry, by the greatest common divisor of these two numbers. So you've taken everything that's common to those numbers out. So it's going to be 1 for sure. Really, what you need to do is find a multiplicative inverse for 20. Right? If you were in high school, you would, at this point, divide through by 20. Can't do that here because we're working in mod 43 world. So we can't divide by 20, but we can multiply by something that will cancel the 20. Okay? And that's what we need to figure out. So how do we do that? Yeah, we have to use the Euclidean algorithm. So we already did it once. This was just